So what I wanted to do in this video is do an example involving Richardson's extrapolation, except using something different than the central divided difference method, which is what I did in the previous Richardson extrapolation video. And to help with this, I'm going to use an exam problem from the past that test on differentiation techniques. So as you can see on the screen, I give you some data in a table where I give you time and pressure, and I tell you that some researcher is interested in knowing how pressure changes with time, so the derivative of pressure with respect to time. And for part A, I say that using the forward divided difference method with h is 0.3 seconds, approximate the first derivative at t equals 1. So I am interested in the derivative at this point. And it says use forward differentiation with an h of 0.3. So that means if I'm going forwards, I will go ahead forwards in time by a distance of 0.3. So I'm going to say that the derivative approximation at some point for forwards is f of x plus h minus f of x over h. And really it should be approximately, right? Because this is an approximation since we have a finite h. So if I want to find the derivative at 1 second, that will be the same as f of 1 plus h, where h is provided, minus f of 1 divided by 0.3. This is the same as f of 1.3 minus f of 1 divided by 0.3. F of 1.3, if we go to the table, is 186.2. And then f of 1 that is given is 172.4 divided by 0.3. We end up with our approximation for our derivative to be 46. And I'll write this as an approximate value for h1. And we'll see why I'm doing that now. But that is our answer for part A. Part B says to perform a second iteration of the forward divided difference method to improve the estimate of the first derivative at t equals 1 second. So if I want to improve the estimate and do forwards again, I have to make h smaller. So with that in mind, that means, given the data, that the only h that I can do is 0.2 because I have to go to the next point. That's how I would improve the estimate. So it's going to say that f prime of 1 for this new h is going to be f of 1.2 minus f of 1 divided by the h value of 0.2. F of 1.2 is 181.5 minus f of 1, which is 172.4, divided by 0.2. I'm going to double check this and make sure this is okay. We'll do that in our calculator. And we get 45.5. So now we're saying that our derivative approximation with the new h is approximately 45.5. And I'll say that this is my approximate value for some second h. So I now have two approximate values, one with h is 0.3 and the other with h is 0.2. If we go to part C, it says using the h values from parts A and B, we're going to derive an equation using Richardson's extrapolation to improve the estimate of the first derivative. So the general idea behind Richardson's extrapolation is to say that I know that the true error is on the order of, considering we are doing forward divided difference, that means that the error is on the order of h. So that true error is going to be something like c times 8, where c is some arbitrary constant. That depends on derivatives and other numbers from the Taylor series. But if we neglect higher order terms, we'll say that the true error is just equal to some constant times h. And I'm going to include what we had before. Maybe I'll just make a little table just to show. When h was 0.3, our approximate value was 46. When it was 0.2, it was 45.5. That's what we just found up here. So I will say that the true error, and maybe I'll say that this is the first one, and this is the second, but the true error for the first one, this is going to be some c times h. And the true error for the second one, if I want to do it in terms of this h, maybe I'll do h1. This could be the same as c times h2. If we were to look at the ratio of these, I can see that h2 is just 2/3 of h1. And the way to get that really is to just do h2 divided by h1. That will tell us that 0.2 over 0.3 is 2/3. So that tells us the relationship between these. So this is the same as c times 2/3 h1. And I'll just write this a little bit differently. I'm going to say that this is 2/3 c h1. This is the error of the second iteration. Now, the thing that will benefit is noting that this term right here is the same as the true error for the first iteration. So I'll say that the true error for the second is going to be 2/3 the true error from the first. And that should make sense, because if I take h and I decrease it by a factor of 2/3, the error for forwards will also reduce by that amount. So now what I can do is use the definition of true error to relate these two. I know that the true error by definition is the true value minus the approximate value, and this is the approximate value as we see here for the second h. That's 2/3 the true value minus the approximate value at the first h. So that's the error for the first iteration. We just have to do some algebra now in order to solve for the true value. Now, this isn't exactly the true value. This is just going to be a better approximation of the true value. But we write it like that based on the definition of the true error. And again, the reason that is because these expressions aren't exactly equal. It's just what we're using if we assume that h is small enough, and we'll neglect all the higher order terms. But maybe what I can do is multiply both sides by 3. If you want to do it like that, we get 3 TV minus 3 AVH2. This will be the same as 2 TV minus 2 AVH1. Again, that's just from multiplying both sides by 3, so those 3's would cancel. And then I can distribute that 2 to both those terms to get that equation that I just wrote. And now all I have to do is do some algebra. I can subtract this 2 TV to the other side. That'll give me TV is equal to 3 times AVH2 minus 2 times AVH1. This will be the same as 3. The approximate value at 2 was 45.5. Minus 2 times the approximate value there. We get, again, this isn't exactly the true value, but this is an improved approximation. If I go through that math, we get 44.5. And that's one way of thinking about Richardson's extrapolation, this idea that if we know how the error changes between two iterations, in this case, I know that the error for the second one is 2/3 of the first because the h decreased by 2/3, we can go ahead and solve for what the true value is. Now, what I would like to do is I'm going to erase this. Let's just keep in mind that that's our answer. And we're going to do this a different way, which is essentially the same, except we don't need to find the ratio of the h's. All we'll do is arbitrarily, let me just do a giant bubble here, is arbitrarily take the ratio of the two errors and write an equation for it. So the true error for the first one we know is going to be something like CH1. The true error for the second one is going to be something like CH2. If I wanted to, I could just divide these arbitrarily. Let's do ET2 over ET1 and say that this is going to be CH2 over CH1. Now, when I do this division, the constants are going to cancel. And now I can substitute in my errors. So the true value minus the approximate value at H2 divided by the true value minus the approximate value at H1. That'll be equal to H2 over H1. And now we can go ahead and do some more algebra. I can go ahead and multiply both sides by H1 and then multiply both sides by this denominator to get rid of all the fractions. So I get H1 TV minus the approximate value at H2. It's going to be H2 times TV minus the approximate value at H1. I can go ahead and distribute the H's, so I'll get TV times H1 minus H1 times the approximate value at H2. I'll get TV times H2 minus H2 times the approximate value at H1. That should be a 1. We would like to get the true value terms on one side. So I'll do H1 times the true value minus H2 times the true value. This will be equal to H1, the approximate value at H2, minus H2, the approximate value at H1. Let's double check to make sure we did that correctly. I'm going to bring this term over to the other side. So I subtract it. That's what gives us this. And then this term I'll add to the other side. That will give us H1, the approximate value at H2, minus this term, which hasn't changed. If I factor out the true value, I will get H1 minus H2 equal to all that stuff. And then if I divide, I will get my approximate value for, or my true value based on these two approximations, where now we will divide by H1 minus H2. And this should give us the same answer. Let's go ahead and check. I'm going to copy this. Maybe I'll paste this up here and make it a little bit smaller. And let's go ahead and delete some of this so I have room here. Okay. So we have all of our H values present. This is going to be H1, which is 0.3 times the approximate value at H2. It's 45.5 minus the H2, which is 0.2, times the approximate value at H1, which is 46, divided by H1 minus H2. If we do that, we get 0.3 times 45.5 minus 0.2 times 46. This is 4.45 in the numerator divided by 0.1. We get our true value as 44.5, which matches the true value that we derived the other way. Again, you can pick your poison. I prefer this because there's not as much manipulation with like the C's and the H's and finding the ratio of the H's. In this case, it's just strictly divide the errors by each other to cancel out the constants, those C's, and then just do a little bit of math. Maybe you don't like the algebra. The algebra here is maybe a little bit more confusing. But if you do it either way, you'll get the same answer. So I hope that this was helpful. If you have any questions, please let me know. Okay, thanks.